So what did you learn from yesterday? B-spline. Any other thoughts? Others? Any one-liner? Anybody want to share quickly? Emphasis on curves and surfaces, and okay, not much on surfaces. Others? What is your takeaway from yesterday's discussion that we had? Transformation. Should summarize in just one liner. Difficult task often. You can keep on saying something, but you study differential geometry, really? That's too far-fetched. Body of surfaces, modeling of surfaces. Okay. Anybody else from here, this side? So what is your takeaway from yesterday's? So what are the key things that we looked at it? Parametric curves, and to an extension it's on surfaces. So basic idea was to give some feel on parametric curves and surfaces. For that matter, which we did not see, it could be extended to solids also. So we saw a single parameter. This is a single parameter implies curves. Two parameter. Then what about solids? Surfaces had how many parameters? Two. Surfaces. Parameter wise how many? U and W is what we discussed, right? So in that case solids, then how many? It will go to a, so that's called as a trivariate surfaces. Okay, so basically what will happen there is that the solids are composed of, imagine the cube that we discussed, right? Cube having a, instead of a plane surfaces, it will all have the Bezier or B-spline surfaces. So that's a solid bounded by set of surfaces, which is what your cube is also. But then what you do additionally in a solid, it always encloses a, how do you define solid? We are going back and back to LKG thing all. Something is watertight. Okay, I think all are confused now. Suddenly if you ask a very fundamental question, then all of us are in different directions. It's understood. Okay. Understood by whom? So it's still not coming. Maybe we'll just many times we'll do this and then come back, then it might be okay. So it's still refusing to come. Yeah, so this is the trick always, so it's always a confusion of which one to start first, whether you put the cable and then start the computer, or first start the computer and then put the cable. Okay, so there is a popular term in computer science or acronym or whatever. So there is something called CG in computer science. So CG refers to what? Okay, CG normally refers to computer graphics. Okay, typically if you go and tell any computer science guy CG, I am doing on CG, then immediately the guy will construe that you are working on computer graphics. Okay, that is a typical thing. So if you tell me that, probably I would little bit imagine it's on a computational geometry. Okay, even then for me CG might still hold as a computer graphics typically, because that is the usual equivalent acronym for that. Okay, so what we are going to look at it is, somebody has some music coming in. Okay, this guy. So we look at computational geometry. So this might be a very new term. I mean, geometry, of course, we all looking at from our schools, right? And computational also we have heard of that term. So what is the combination? Okay, computational geometry. Okay, so this topic, I think, which is relatively new, probably 40 years old or around that, maybe little more than that. So this deals particularly with the discrete entities, something called as set of points, or a polygon, which is very different from what we saw yesterday. Yesterday what did we see? What did we see yesterday? Okay, parametric curves and surfaces, which are all continuous surfaces, continuous curves and surfaces, because given any value for u at whatever resolution, we just say it is between 0 to 1, but you can have 0.00000001 and still we have a point on a curve or a surface, right. So, that is basically in a nutshell, it is a continuous curves and surfaces, okay. That is what we define by an equation, and then we come out with any point on a curve or a surface depending on the parametric value. So, these guys are exactly opposite to them. So, this is only points, okay, or connecting set of points, then it is called as what? If you connect set of points and then let us say it becomes closed, then what is that shape that you call that as? Polygon. Okay, do not think too much, it is also a simple question on that. So, we will essentially this subject deals with points, it could be in 2D or a 3D or a polygons. What is the corresponding name in 3D? Polygons, how do you describe in 3D? Polyhedrons, okay. And of course, if you have a plane, so how do you go for higher dimensional planes? So, how do you describe them? Hyperplane, okay. So, I think he is a math guy and he is clearly showing the terminologies. Yes, typically these are all used only in the math kind of a thing, and this is actually lot of math in it, which I am safely negotiating, okay. So, little bit of thinking that either you will go to sleep or I will go to sleep, or maybe both of us might go to sleep. So, so let us look at some very interesting problems in geometry. I think completely fascinating and defying our own thinking. You will see that. So, you can note down, this is basically the slides I was forced to use because of turning to an online lectures in the last semester, which I usually do not use slides completely on board, but since that facility was not available or it was difficult to do that. So, it turned out to some slides, but it may not have too much on the slides actually. So, but this is my course on ED 5310 on the engineering design department. So, if you go to course page, lot of things are available you can make use of, and we will also discuss some of them here. So, basically what are the objectives broadly? Of course, we cannot cover all that in today's thing alone. This is done over a period of 4 months or 3.5 months. So, we will just see some very interesting algorithmic paradigms. That means what? If you are given any other problem also, you can make use of this idea to solve that problem. So, it is like a general technique. So, not necessarily restricted to a particular geometric problem. Okay, this second point which we may not be able to see, but there is a lot of relation between geometry and the machine learning. So, if you have heard of the terms like SVM, have you heard of the terms like SVM? You must have heard, right? So, all are data science enthusiasts anyway. So, we all have heard that. So, SVM, what is it? Support vector machine. So, they have very close relation to convex hull that we saw yesterday, the convex hull part, and we will see that I will probably give you some example problems where you can develop some new algorithms could possibly be, think of at least in that direction. So, if you want to go to my web page, so for this course you see the last one on that. So, yeah, we could do several things, and these are the learning outcomes, which of course happens over a period of 3.5 months. We will try to see how much we can achieve in today's thing on that. So, okay, this is an entire course content if you want to do, and this is not very relevant here, but for just for completeness, if you want to do more and more, you can go to my web page. So, a lot of things that I also little bit cover on data structures part, just to give a feel for other people who are not from the CS background. So, some little bit on the data structure side that I usually cover, but I think here we may not be able to do. So, we will try to see that we will just keep that part aside as such. Okay, these are the two textbooks that we typically use, and primarily the computational geometry in C by Oruk. So, if you go to Oruk's page, fantastic guy, you can see that he has a lot of other books as well, and I like this his book, and there are several other books in computational geometry, And of course, if you are in machine learning already, you can look at the second. I somehow like the second book because it's this book on machine learning is more on application perspective from fundamentals, and not suddenly talk of too much and then get lost. So the first, I think both books, I think Indian edition is not available if I remember correctly, but by now you all know how to get some PDF from somewhere. So I think we'll get some details of both books elsewhere on that. So the second book, I think the second edition is available only as a thing and not as PDF as far as I searched. So even computational geometry by Oruk is actually kind of available in some sense. So you can go to his web page as well and interesting details. So obviously, there are several other resources that you can look at it. So if you go to Oruk's web page, I think he got fed up possibly, and then he put the entire book on art gallery problems as downloadable. So his entire book is available, not this book which I told on, not on computational geometry in C, but it's on art gallery theorems and algorithms. We'll see why a book is there, and we could actually see that a little later on there could be several books written on this topic, not just one book on that. Okay, there's so much to it, and then we can actually develop few more books on that. And then there's another popular book called as Debug, 4-author book, the second one on computational geometry. Then we have this Preparata and Shamos who are kind of one of the forefathers of this field called computational geometry, and they also have a book. So many things actually I pick up from several books, so it's not just one book that I follow typically, but majority will be from Oruk book on that. And then there are some book on, if you are familiar with, if your CS department, you should be familiar with some on data structures, algorithms and so on, which are very much needed for this subject actually. If you want to really do something, then you have to learn them as well. So there are popular libraries like the one that we saw yesterday. What was the library that we saw yesterday, or more on open source? That is GU IRIT, which basically is a graphical user interface for IRIT. So the IRIT is the main modeling system, and it was brought as a GUI as a GU IRIT and all. Okay, but IRIT itself as a completely open source, and see these are also open source. I think libiGL, both are written in C++. I think libiGL, I think both Python bindings are available. I think at least for libiGL it is there. I think Seagull also, I guess it has come in Python nowadays. So you could use both in C++ or in Python. Yeah, so of course this we already know. So I always have my classes as an interactive class, so whichever subject I teach, right from first year course to last year course. And the only one thing that usually missing is that you people never ask any questions, so which is continuing wherever the subjects are being taught. And typically these subjects require some good programming. Okay, if you really want to implement something, learn something, you have to pick up your programming skills. Python is kind of one way, but Python alone will not stand. I think it's just recommend still go to C++ at least. Java, I don't know much on that, so Java is also okay, but you can. So these are a lot of things are on C++ actually. Okay, so the Python thing came little later, as that's the thing being popular now on that. Okay, so maintain this here also as much as possible. So any questions? Anything that you want to ask? No? Okay. Okay, so we will start with this very interesting problem, okay, called as the art gallery problem. Okay, I think I don't have anything further slides apart from this title, I think, but so now what is this problem? Okay, it looks like a very vague. You all know art gallery, right? In a sense, of course, we might have never gone to an art gallery or a museum composing of arts, precious paintings and so on, but there are lots of counterpart problems in any field of engineering that you can think of. Science I am not sure, but of course everything comes out of science in some sense. So what is the idea in this problem? Okay, so now you are in this room, correct? So the room is in a very different shape though. So how many cameras do you think is required for this room? Depends on what? Field of view depends also on the field of view. Okay, now you bring an assumption that the camera can, let us say, see infinite distance or something like that. Let us say you bring a theoretical assumption. So, now based on that, how many cameras you think you require? Any answer? At least 3. Any other answers? Infinitely forward. Okay, field of view, or also let us say that it can cover 180-degree, means it could cover most of them typically, right? Yeah. So, 1 is enough. So, if you bring that field of view down, you may have, but where will you put that? Is really 1 is enough? Because this room is little bit, is it straight or curved? Straight, are you sure? Everybody is now confused on that. I mean, the chairs are arranged or the tables are arranged on a, maybe on a circular fashion or an arc, but the room, I think it's still in a straight one answer, right. So, he is saying 1 is sufficient, and where would you put that one camera? Above the projector. So, then anybody can come in and go out and do something and then do not care. At the back, in the middle, okay. One here also. Why? I mean, you can always put 1,000 cameras, right. So, the point is you are trying to fix as much as less as possible, not as much as possible. So 1 is sufficient, I think, or maybe at the max 2. Okay. So, let us say maybe 2 should definitely be okay, not more than 2 is probably required in any case on that. Okay. So, now what is another similar problem? You have these lights, right. Now, how many lights are required to cover this room? Depends upon, okay, depends upon the intensity profile of each bulb. So, there is an intensity profile of each bulb. So, under that you can still figure out how many lights are required, because you can see that based on all the intensity profile, you could try to cover this entire room with certain number of lights. Okay, this is the same problem in your sensor networks also, like you have your mobile phone tower. So, how many towers are required and how do you place the towers, so that the number of towers are minimized. Okay, this is again problem in, let us say, electrical. Okay. So, the light problem, I do not know which department it belongs to, camera one also I do not. So, these are all very geometry problems spread across any field that you can think of, not necessarily electrical, mechanical, and not necessarily computer science also. But since lot of other aspects from computer science are being used, so it is typically in a computational computer science department on that, but it could be done by anybody else as such on that. Okay. So, there are several problems like that, and here, okay, this is a problem, art gallery problem. So, what is the problem? You have like a security, we have to just let us say that this is a museum set of walls you have, and you have a lot of paintings. Okay, this is a simple shaped loom, let us say, but how many guards are required? Security guards are required to cover these paintings. Okay. So, that is the whole idea. So, basically the art gallery problem is a security guard problem. The security guard is there everywhere, right. You can have it in your house. Okay. So, how many security guards are required to, so if you go to a palace, okay, so that security guard is not usually inside, where they are at the outside. So, that problem is called as a fortress problem, which is again the, so all actually come under a broad aspect of the visibility problem. So, everything is a visibility problem. Basically, it says how much you are trying to cover. So, whether it is a security guard guy, or whether it is a light bulb problem, or a camera problem, or a sensor problem, all could be classified as a visibility problem. Okay. And there is something called as a visibility graph, which I might touch upon little later on. Okay. Now, what is it we have, we are trying to solve here? Okay. We are trying to solve as an art gallery problem, and we will see some simple condition. I mean, I do not think we can draw a 3D model and then try to figure out all that. Okay. But the problem will be very, very haunting the moment you go from 2D to 3D, which I will try to demonstrate little bit on that. Okay. So, now let us quickly come back to this art gallery problem. So, I have not still exactly phrased the problem. Okay. The minimization problem in all these is actually an NP-hard problem, if you know what an NP-hard problem is. Okay. If you are from computer science, you can understand that. P versus NP. Okay. So, but anyway, that things aside, that means like it is kind of difficult to solve in a very algorithmic way. That is the usual idea. Not every problem could be solved. It's more like a greedy approach, what people like a trial and error approach usually. Okay. So, now let us just start with that. So, we will just solve this problem for a simple polygon. Okay. So, what is the meaning of a simple polygon? So, can you draw some simple polygon on your notebook? Pentagon? What about you? Triangle? Square? So, can all of you draw one shape which you call or which you classify it as a simple polygon? One easily drawn? Everybody? Okay, you have drawn some simple polygon. So, can you also draw something which you would consider as not a simple polygon? Yeah, so that is what you only, when I say simple, you draw something, right? But now, but you never asked what is simple. Now, if I say that I am asking you to draw a not a simple polygon, then you suddenly ask what is simple polygon. So, try it also draw that not a simple polygon. 2D only. Polygon means it is always 2D. Okay. So, what do you think it is not a simple polygon? Star. Okay. Now you have said there is some simple polygon notion you have, you also have a notion of not a simple polygon. So, now you define that what a simple polygon is. So, how do you define a simple polygon? So, can you put up a definition on your notebook? So, what is a simple polygon? If you draw, you will all draw something on that. And when I asked not a simple polygon, he immediately jumped and asked, said you have to define simple polygon, but he never asked that before.
A polygon edges doesn't intersect each other and the whole shape is convex in nature. Is a simple polygon.
Kind of okay, but yet see these suppose if you take these so called two adjacent edges, where do they intersect? So you have to be little bit clear on that. So, non adjacent edges do not intersect, whereas the adjacent edges intersect only at their respective vertices on that. Okay, and it is always, it need to be convex, not necessary. Simple polygons need not be only a convex one. You can have a non-convex polygon also. So, can you draw one non-convex polygon quickly? So, it need not be a non-convex polygon. Yeah, so easily you can draw one non-convex polygon. There also you will see that. So, what the polygon is basically a set of vertices and edges, but it is not just any set of vertices and edges. It has to be an ordered set of vertices and edges in such a way like the adjacent edges intersect only at the vertex and non-adjacent edges do not intersect. Okay, and they always form, they are always closed. Okay, we do not consider an open, like what we saw as a control polygon yesterday is not closed typically. We just use the word control polygon just to distinguish from the usual polygon that we use that on that. I mean, it is the Wien term being used on that. So, any polygon we will always see that it has a closed or not. So, this is simple, right? What is the big deal in an art gallery problem, right? Where is art gallery here on that? Okay. Now, let us just increase that and try to go deeper, and then we will define the problem better. Okay. Now, you are assuming that your museum or your art gallery is in the shape of a polygon. Okay. So, what is the simplest polygon you can think of? Triangle. Okay. We cannot things, we cannot prove anything less than that. Apparently, I do not know whether you people know Jordan curve theorem. You know Jordan curve theorem? Okay. So, the Jordan curve theorem is very simple. Any closed curve divides the space into exterior and interior, and you should prove this statement. So, any closed curve like a triangle that you have will divide that space into interior and exterior. This seems so obvious, right? I mean, what else can it do on that? But it's so it's just you have to prove this statement. Apparently, it took few centuries to prove this statement. You have to bring in some topology guy to explain that. So I'll just leave it for those guys to explain that better on that. Okay, now we'll come back to this problem of so-called art gallery problem. So you have a triangle. Remember what is it trying? What is it we are trying to give? We are trying to put security guards that will man the edges, so to speak, of the polygon. That's what we are trying to do. So now go to your notebook and tell me how many security guards are required, and what are the assumptions under which you are telling that many number. How many security guards are required to cover this entire triangle, which is interior? We are not looking at the exterior coverage. Okay. So how many security guards are required? 3, 1. All other guys are looking very puzzled. How many? 1. Okay. 1 is required. That's more than required for maybe. I mean, 1 is sufficient at least, right? So all of us are convinced that 1 is sufficient, only 1 guard. So the assumption is what? So I have a security guard, let us say, in one of the corners or vertices of that guard, and I am covering the thing. So what is it you are looking at from the guard's perspective? Yeah, so the guard can look through the entire field of view if you generalize that, and you know, but then the guard cannot see through the edges. Okay, the walls are opaque. And then you, let us say if you little bit take a complicated shape, we may have to assume that the guard can rotate fast 360 degrees, so that he can cover the entire space on that. Okay, otherwise that will also have certain issues, correct. So now let me just put down that, and we will see that. So there are how many vertices in this shape that you have considered? 3 vertices, and correspondingly how many edges? 3. Okay, so these are all counterpart wise, they will be always remain the same, which is n number of vertices. So we can see that we will just note it as guard. So guard for 3 vertex polygon, what is your number? We can always go 100 also, okay, but we are looking at what could be the as minimum number as possible, but you can see that that could be little difficult. So we can see that only 1 guard is sufficient for this guy. Now you go to the next guy. What is the next step? From 3 vertex polygon to a 4 vertex polygon you go. Okay. So now in a 4 vertex polygon, can you do some deliberation and tell me what will be this G of 4? Any shape? It could be non-convex also, but non-convex, everybody is thinking that 1 is okay for non-convex. See, if I threaten with more questions, then you will suddenly change the answer. The guard only cannot see through the walls or see through the edges, that he can crease the edges, that is okay. But why you require more than 1? Now everybody is okay, you have a shape like this, which is what everybody is confused now. Okay, now how many guards are required? So if you place here, obviously that guy cannot cover everything, because this region he cannot see, right, he or she cannot see. So and similarly if I have, so what about if I place here, you can see, right. What about if you place here? Yeah, also yes, that is why I said you can rotate, the guard can rotate so fast 360 degrees, so that you can cover the thing in. So the time we do not consider that. So you can see that G of 4 is also what? G of 4 is also 1. So what about the next step? So take a 5 vertex polygon. How many? So what is your answer for a 5 vertex polygon? A polygon should be having 5 vertices, that need not be necessarily a convex polygon, okay. So how many vertices you will require? 1. You are sure that you do not require more than 1 for a polygon of any configuration with 5 vertices? But why are you drawing on hand? You have the notebook already. One is enough?
No.
No? Why two?
Okay, yeah,
You can use one.
we can use this one.
Okay, you are now boiling down from 2 to 1. Others? 1? Is it sufficient? Okay, so now all are convinced. So now what is G of phi? Okay, G of phi is also 1 apparently, it looks like. So what will be G of 6 then? What will be G of 6? 2? Well, suppose if you take a hexagon, how many vertices it has? 6. How many gods you will require? There you will require only one, but we are not talking about that case. We are talking about, could there be any other configuration of 6 vertex polygon, okay, or a polygon of 6 vertices, where it could require more than one? Is it true? All are convinced? Hmm? Okay, yeah, correct. It looks like that, yeah. There also it could be difficult, yeah, yes. Okay, so you can also at this instance you can think we are putting the god on the vertices, but it not necessarily so. Okay, but you can see that G of 6 will be 2, but there may be some 6 vertex polygon that may require only one. Which one is that?
Any concave.
Any convex, like a hexagon. Okay, so like a hexagon will require only one, that is also a polygon of 6 vertices. Okay, but then there are some polygons where it will require more than one, which are also of 6 vertices. Okay, so that means what G of 6 is going to be 2. So what could be an example for that? Okay, something like this. How many vertices it has? Are you sure I have only drawn 6 vertices? Hmm? Okay, so how many gods you require here? So it cannot be done with one, no matter which vertex you try on that. Okay. So G of 6 is 2. So what about, can you try for G of 7, G of 8? So what is your number? Two again? Sure? No 3? What about G of 8? You have to try, you should try that and tell. Hmm? G of 8 will require 3. Can you try that and see that whether it is happening? You tell me whether you require 3. You put the gods and show me that you need 3. So can you do better with some other place so that you could go from 3 to 2? In the same shape. So can you just little bit think about it? You could pick those two and then that will become only 2. Okay. Of course, as I said, you can go more than 2, that is okay. You can go to 3, 4, 10, 100, all that are okay.
I think that every increment of 4 vertex, we need one more guard.
Okay, so okay, kind of your conjecture is kind of right, yeah. So then what will be G of 7? 2. So what about G of 8? G of 8 is 2, that is what he wanted to. So what about G of 9? 2. So can you just show that? G of 9 is also 2. So, G of 9 is also 2. So, can you just show that, or is there any other configuration that you may require more than 2? It requires 3. Show the shape. Okay. Really, in your shape it looks like 2 is okay for me. Show that again. In this case also it looks like 3 is sufficient, 2 is sufficient for me. 1 and 2. In the way that you have drawn, it looks 2 is sufficient for me. Is that right?
It's not necessary to put it in vertex.
If some vertices you think that it may require 3, maybe in some other portions if you place it may require 2. But are you sure that you require only 2? Nobody has found a polygon that will require more than 2 of 9 vertices. Nobody? Show that. No, here also 2 would be okay. You put one in that reflex vertex, that L side, and only in that cross, then the 2 is okay. You put in those 2 you require. That is interesting, right? So, you have to just look at. So, nobody has a case where you require 3 guards for 9 vertices. Really? So, put all Rangoli on your notebook and then all kinds of Rangoli you try, and then let me know. Some Rangoli may require 3. That is why you have to think little bit more. So, the moment you think on it is all reproducing the same thing again, right? You are trying harder and harder, but eventually turning out to be the same shape. This looks like you will require, this also requires only 2, unfortunately. Isn't it? This also requires only 2. Very fascinating. You tried with so much thinking and then eventually turned out. No intersectant, only simple polygon. That guy threatened me with the definition of simple polygon. You haven't told that. So, this is simple polygon only. Don't go with the star or, but it won't be convex. By that, by now you know that it's not going to be convex. So, it has to be a non-convex shape or a concave shape. Why? But tell how many vertices you have. You should not have 10 vertices there. Number from 0 to 8. Number in anti-clockwise direction, starting with any vertex. 9. Okay. This requires 3. No. No, you can put one here and one here. Like one here and then one here.
It's always thinking about some snake patterns.
Right. So, how do you, nobody has got a shape which require, okay, he seemed to have got something. So, you want to go and draw that quickly and let the others also. So, you also draw your Rangoli pattern on the note on the board. So, let us verify that whether you are indeed true, because sometimes you may think that you require 3, but then it could be end up in only 2. So, mark the vertices from 0 to, in the anti-clockwise direction, start any vertex with 0 and then go in the anti-clockwise direction. Okay, whatever I said, he didn't follow. Okay. I said you start with 0 and go in the anti-clockwise direction. He again started with 1 and going in the clockwise direction. So go in the anti-clockwise direction. Which is will be the next vertex in the counterclockwise direction? So he just got confused and he started with another convenient vertex, but not the one that he actually started with. Okay, 0 to 8, that is fine. That means it has a 9 vertex polygon. So he is claiming that this 9 vertex polygon will require 3 gods. Is that correct? Hmm? Oh my God, 2 is sufficient, yeah. 2 is sufficient or may not be actually, right? Yeah, 2 may not be sufficient here. No, no, 1 and 3 will not cover. 1 and 3 will have some region somewhere here that will not cover, because if you put a ray from here and ray from here, there will be some region that will not be covered by both, right? Somewhere here you mean? That will become and somewhere here and then somewhere here. Yeah, I think even that looks difficult in this case. But you should not change the number of that shouldn't change the number of vertices. It looks little difficult on this one. Yeah, I think that there is a difference between when you place on edges and on vertices. Some slight difference is there on that. So barring that, I think in this case, if you pick 1 and 3, you can clearly see that there will be some regions that are not going to be covered by both 1 and 3. I think all of you are able to see that. Okay, so if you just draw a ray from here, there is something here. Okay, and if you draw one from here, so this region is kind of not covered by both 1 and 3. Okay. So do you guys, any other guys have any different shape? Show your own Rangoli skills. Huh? That's okay, you can just go draw that. Anybody want to go and draw and show your skills? So by this, what is the conclusion now? Your conjecture is wrong. Okay, that is one conclusion. But you can just modify, you are close. You just have to little bit refine that. So you just have, if you little bit refine that, so what is G of 9? Every 3 is going. So what is G of 9? 3. So now can you say what is G of 10? 10 will be 3, 11, 3, 12, 12 will be 4. What is G of 100? 100 by? So 100 by 3, basically you have to take the integer component of that 100 by 3. So that is exactly what this. So if you keep on going, of course if you want to draw a shape, it could be a little difficult on that. So if you have any G of n, then basically we can kind of conclude that. So you can see that as he said, kind of after every 3 guys, it seems to change to the next number. So what will be G of 100 in that case? So you can see that 6 then becomes 2, 9 becomes 3, then 12 is likely to become 4, and so this is a conjecture. Basically you do this as, what is this symbol? Yeah, but what is the name for this? It is called as floor. So floor of n by 3 is what the conjecture is. Based on all our Rangoli patterns, we are trying to conjecture that it is a n by 3.